I'd just like to welcome Julia, welcome her back. Glad to have you here again, and looking forward to your talk.
Okay, thank you. So is this working properly? Okay. So I'm going, sorry, my name is Julia Lawall. I'm from INRIA in Paris. I'm going to be talking about graphing tools for scheduler tracing. This is a version 2 of a talk that I gave at FOSDEM. If you want to see the FOSDEM one, you can go find that one online. The beginning is the same, the rest it changes in the middle. Okay, so basically the overview of this talk, first I'm going to talk kind of at a high level, what is a scheduler, what is impact on application performance. Then I'll talk a bit about briefly about some existing tools for understanding the performance, and then I will talk about the tools that we're proposing. And basically my interest in this talk is large multi-core machines. All the examples will be on a 128, it's a 4-socket Intel server with 128 hardware threads, which for simplicity, I'll just say 128 cores. So the task scheduler, the Linux kernel, what does it do? Basically, it has 2 purposes. The first one, or one of them, is to, when a task wakes up, or when it's created, or when it gets load balanced, to choose what core it should be running on. And the other one is when a core becomes idle, to see which task should run next. Basically, if you're familiar with the Linux kernel code, we're interested in the files core.c and fair.c. And in this talk, we're only interested in the first part, the placement part. So who should be running where, basically? So the question is, how can that have an impact on performance? So basically, at a high level, a scheduler has to make decisions. It doesn't have very much information when it's making these decisions. It may know something about the recent behavior, but that's not necessarily going to be the future behavior. And it also needs to make decisions fairly quickly. There's some people who are very concerned about scheduler latency. There are other people who are not concerned at all, but some people are concerned. And basically, these poor decisions can slow tasks down. And they can also have a long-term effect. If you have several tasks that end up running on the same core, they might tend to stay there for a while, and that will have quite a unfortunate impact. So I'll talk about 2 issues. The first one is what's called work conservation. So work conservation is, you can think of it as conserving the ability to do work. So we have a little machine. It has 4 cores, and all these cores are empty. So we have a task that wakes up, and we can ask ourselves, where should we put it? And maybe this task is actually just being created for the first time. We don't really have any information about what it's going to do, so we could perhaps put it anywhere. Let's put it on core 0. Now another task wakes up, T2, and we ask ourselves again, where should we put it? And it might seem fairly intuitive that core 1, core 2, or core 3 might be a good choice. Nothing is running there right now. If we put the task there, it can run immediately. On the other hand, it might seem fairly intuitive also that core 0 is not a good choice because something is already running there, and if T2 wants to run, it's going to have to wait. So this is the idea of work conservation, that no core should be overloaded if any core is idle. So intuitively, this might seem like a good idea. On the other hand, the Linux kernel scheduler is a completely distributed scheduler. If a core is waking up some task and wants to figure out where to put it, and if they're going to have to search over all 128 cores to find the idle one, that might be a bit expensive. So the Linux kernel scheduler is actually not work conserving. So another issue is locality. We have some task T1 that's already running on core 0, and now some other task wakes up. Where should we put it? And so we might be interested in knowing some things about what T2 is going to do. If T2 has previously run on some core, or at least on some socket, this is a 2-socket machine, if it's previously run on one of those sockets and it has allocated a lot of memory on that socket, it might be a good idea to put it back in that place. Or if it's going to communicate in the future a lot with T1, it might also be good to put it on core 1 because then it will be able to share caches and so on with T1. And if we put it on core 2 or core 3, that might cause some slowdowns. So basically what we've seen is that the task scheduler can have an impact on performance for those reasons that I've shown and also for other reasons. The challenge is that the task scheduler is buried deeply into the operating system. And so from when you're at the user level with running your application, trying to understand its performance, it might not be so easy to actually figure out what the scheduler is doing at what time and why and so on. So fortunately, some people have encountered that problem before and some help exists. So there are trace points in the kernel that collect information about various things that happen. And then trace command is a user level tool that will activate different trace points and cause things to happen and make a tracing file that records all the information. So here I have a command line for just tracing the scheduler related events. Basically we say trace command record, and then we have the -e for the events we're interested in. This is to make it a bit more quiet. This is the output file. This is the program you want to run. And if you run this, then we get a trace that looks like this. But this is just a very, very tiny extract of a trace. So traces may be quite enormous, gigabytes of data. So basically this trace is organized it's organized chronologically. So you can see what happens before what. That can be useful, but on the other hand, all the information about what's happening on different cores is all mixed up, and all information about what's happening but for different processes is all mixed up. So basically we see here, this is the task that's running at the moment that's causing this event. This is the core where it's happening, so we see different cores getting mixed up here in the list. This is the time, this is the event of interest at the moment, and this is just various other information. So for example, here for the switch, we can see here we're switching from swapper, which is the idle task, to something called C1 compiler thread. So these traces, they have all the information, but they can be very tedious to look through. You tend to get kind of lost in what's going on. So another tool has also been developed, which is called Kernel Shark, and this is a graphical front end for the same traces that we were seeing before. So you have the trace information here at the bottom of your screen. Right here, this is basically the same information we saw before. But at the top of the screen, you have some nicer graphical display. Basically, on the y-axis, you have the CPUs, or you have the different tasks. There are different options. And the x-axis, you have time. And then you have different colors and little marks to show that certain tasks are running. And you can zoom over these things and find out a bit more about what's going on. You can also zoom over different regions, and then you can zoom in on what's happening at some particular time. So in some sense, it's a very nice tool because you can really see at a fine level of detail what's going on. On the other hand, it's hard to get really an overview of what's going on your machine. So it's got kind of a spacious layout. First, we have the top half and the bottom half, and even between the different cores, there's kind of a lot of white space. So if you have 128 cores, even if you have a reasonably large screen, you just can't really get a feel for what's going on. So what we're interested in is making some other tools that would be complementary to Kernel Shark that can kind of give you more of a big picture and help you find out where are the parts you should zoom in on and so on. So basically what we want to be able to see all the activity on all the cores at once. And another thing that I found extremely convenient in my own work, and hence it became a priority, was to produce files that I could save and share and refer to and so on. So I just want to produce PDF files. I don't want a GUI that only exists while I'm using the GUI. On the other hand, what my colleagues often complain about is that the tool is not at all interactive. You just spit out PDF files. You have to run a command line to generate each one of them. So it's definitely a trade-off. Kernel Shark is definitely good when you know where you're going and what you want to look at, and you want to zoom, 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 and see more stuff. So it's very complementary. So I'm just going to talk about 3 tools in this talk. I've made lots of other tools. Like every time I think of some property that I want to understand, I kind of have to make another tool for it. But these 3 tools have been kind of proved their usefulness over time. So the first one is dat2graph. And dat2graph is sort of like, dat is the name of the files that the trace command produces, and graph will have a graph. This is basically like Kernel Shark, only just in a more compressed format. So basically what we have is we have our cores on the left-hand side, we have time on the right-hand side, and we have edges like this task is running from this point in time to this point in time. So that gives you a fairly fine-grained look at what's going on. Another tool that I found very useful is called running weighting. This is a line graph. So data graph is very precise, and running weighting is giving you just a very generic overview. You just want to know how many tasks are running on the machine at any particular point in time, and additionally, how many tasks are waiting. So data graph shows you what's running, but you have no idea how many things are waiting on those cores. So problems arise when you have things that are waiting. You would hope that they're running, and so that's why this kind of graph is useful. And then I made another tool which is called Stepper, and Stepper just takes those events in the trace and just steps through them and shows the entire state of the machine at any point. So that's extremely fine-grained, and that one actually is interactive. So all the tools are publicly available. I'll put the link up at the end of the talk. So we're going to do in the rest of the talk is look at a case study where we use these tools to try to find out what's going wrong in the performance of an application. And so the application I've chosen is a very simple one. It's a NAS benchmark suite. So these are a bunch of little programs that do kind of typical things for high-performance computing. So maybe FFT or whatever. The one I've picked is called UA. It says it's an unstructured adaptive match dynamic, and I have no idea what this means. Basically, the interesting thing from a scheduling point of view is that this application has n tasks, and we want them to run on n cores. So intuitively, there should be no scheduling problem. Our tasks should just run happily and terminate after a while, and everything should be okay. I also use the same benchmark in the talk at FOSDEM. So this is the observations I had at FOSDEM. So what I've done here is I've just run the application 10 times and made a graph of the execution time. This is from an old version of Linux 5.10 versus Linux 5.11. Or actually, I made a patch that makes an impact on 5.11, so it's before my patch and after my patch. So basically what you see, if you look at these blue lines, so I've sorted the runs by increasing runtime, so they always go up to the right like this. Basically, you can see with these blue lines, in 5.10, we can have good performance, as in these cases. But like 3 out of the 10 runs have quite worse performance. Somehow there's a big gap here between the kind of okay performance and the bad performance. And if you compare this one, the slowest one, to the fastest one, then it's about 50% slower. So it seemed like something was not as good as one might hope. And so the patch that I made somehow favors putting a task that's waking on a bit more on the place where it was before, and that kind of causes fewer things to have to move around, and then we get better performance. You can see, though, it still goes a bit up as you look off to the right-hand side, so perhaps there was still something was not completely ideal in 5.11. So in preparing this talk, I thought perhaps you're not so interested in 5.10 and 5.11 anymore, so we'll do Linux 6.3. So here I'm just comparing 5.11, so after my patch, with 6.3. And so you can see that maybe the performance has, I don't know, something happened along the way. Actually, 5.11 itself was not that great, because you can see there's another one of these gaps, and it can also have kind of worse performance. But 6.3 is like, if we take these and we sort them by increasing runtime, the 6.3 is always worse. And this one here is like twice as bad as the fastest one. So it seemed like it could be interesting to see what's going on. Of course, one thing I could have done, which I did not do because that wasn't the focus of the talk, I could have used git bisect to find the patch where the performance goes bad. It would be a bit tedious in this case because we can see that most of the time in here the performance is not that horrible. There's just one pathological case. So you would have to perhaps do a lot of runs to be able to decide whether we're good or bad for each case. But there's also the issue that with git bisect, you don't always necessarily end up in the right place, and you also once you end up in the right place, you have to interpret somehow what that patch does and how it relates to your code. So I think it's valuable both to understand what the scheduler is actually doing and what has happened in the Linux kernel source code. So we're just doing one half of it, which is understanding what's going on. So just to kind of get to know the benchmark, one thing that's sort of obvious to do with this kind of scientific computing kernel thing is just, I mean, HPC people, they're not letting the Linux kernel scheduler deal with their code. They're just pinning the threads to the cores and getting what they expect will be the optimal performance. So we can try doing the pinning to see what happens. So I have 3 choices for pinning. One of them is, as the threads are forked, I just do kind of a round robin between my 4 sockets. And one of them is I ensure that I do the same kind of thing for the sockets, but I ensure that I don't ensure that they're in any kind of order within a socket. So actually, both of those cases are optimal. They are at 14 seconds, which is faster than any of the runs that we've seen so far. Another option is just to randomly pin the threads to the different cores. And there, again, there's no like big jumps in the performance in this case, but the performance is always the same, and it's always worse than the case when we're pinned in some organized way within the sockets. So basically what this suggests is that this benchmark is sensitive in some way to locality. Either it's communication between different processes or it's somehow memory that's shared and so on. So that's just the information, but we're interested in the talk though is what happens, why does Linux kernel scheduler not do the right thing for these tasks? So now we're going to look at the result of datagraph. So what I have done here, basically this is the simplest use of datagraph. So we have our trace and we want to produce a graph and it will show what's running at what time on what core. So I have my trace file. It has a big name that means something to me, but it's not very important. So datagraph in the file, and then I get a graph here. So actually, I have not run exactly this command line. I ran with this on this file and also on the slowest file. So when you give multiple files, then it will ensure that everybody has the same x-axis, and that's why the x-axis goes up to this number here, which is the duration of the slow run. And then you can compare your files and see this one's fast, this one's slow, what's going on, and so on. So basically, this run is about 20 seconds. This is basically what we get when we pin the threads to the cores in a random way. And we can see that the threads mostly just stay in the same place, although there's 2 main places here where they move around a lot. Remember, we have only n threads and n cores. We would expect, with a little knowledge of the application, that they would always just stay in the same place all the time. That seems like the ideal thing to do. So this is the fast run, and then now we can look at the slow run, the one that is like twice as long. And now you can see that like things are just moving around all over the place. And if I have annotated this, because I'm not sure it's so easy to see, there's a bunch of places in the graph here that are white. And these places are where nothing is happening at the moment on that particular core. And that seems very unintuitive because we have n threads and n cores and they're all running all the time. And so we should expect that there shouldn't be any places where nothing is happening. And actually, even the fast run has some gaps, but not so many of them, at least not so many of them that we can see. And they're not as big. If we look at the slow run, some of them, here we're up to multiple seconds of inactivity. So the question is, what about these gaps? So what's the impact of them? So in some cases, certainly some applications, if you make some traces, some places will be white because there's just nothing that these threads have to do. So then there's no performance impact. That's just how things are. And the other situation is that some cores are overloaded and some other cores are idle. That's what I mentioned before about work conservation. And this will cause a potential slowdown. So now we can we have this hypothesis, we want to see, are things overloaded, is that our problem, or is the situation something else? So for that, we can use this running waiting graph. So here I have running waiting, and I just gave it my file name. And here the graph is, it has basically 3 kinds of lines. So we have on the y-axis, we have a number of threads. On x-axis, we have the time. The green lines indicate how many things are running. So we have this green line which goes up and down, like many things are running, fewer things are running, and so on. We have a black dotted horizontal line here, and this is how many cores there are on the machine. So there are 128 cores. Obviously, the green line will never go above 128 because we can't run more than 128 things at the same time. And then above, we have some little red lines, and the red lines indicate how many overloaded things there are. And so when you look at this thing, you might be a bit surprised because actually this is the fast run, this is the one that's going well, and we seem to have lots of overloading. Actually, we seem to have a lot of things going on beyond the number of cores on the machine. And so actually, you have to kind of take this as a grain of salt. The graphs have a certain level of granularity that they can show. And so there may be many overloads, but they may be very short. So you have other things that are happening on your machine, some K-worker, some other kind of daemons, and those are causing all of those things. So there's another option for running waiting, which is forked, and that is only going to show the tasks that are forked at the moment. So this is more like what one would expect, which is that most of the time, but not all the time, we're up here at the 128 level. And we only have a few little tiny red things. Basically, green is good in this case, and red is bad. So you just look at the graph and see where is it red. So this does not seem too alarming. On the other hand, if we look at the slow one, then it looks like this. And so here you have to really focus on that black dotted line. So we have a few little red things that are above the line. Okay, so if you have more things than you have cores, obviously you'll have some things that have to wait. But what's more alarming is that we have these huge regions here, sometimes one case up to 10 seconds, where we have little bits of red underneath the dotted line. And so those are all cases where we have overloading. We only are getting 127 or 126 threads that are running, and those little red ones are the ones that are having to wait for those running ones to complete. So now we can go back to datagraph and try to see what's going on in these regions that are have their little bits of overloading. I mean, on the one hand, we had our gaps, and on the other hand, we have our overloading. And so what I'm doing is zooming in on a region where we have a gap. So this is like the beginning of a gap. And actually, I'm using the fast run just because it has fewer gaps, and so it's easier to study. So here we are back again with datagraph. Here's our trace file. We have, this is how we have to zoom in. So we specify the starting time and the ending time. And then there's an option which is color by command. So before we had the little horizontal lines that were colored by the PID, and now they're colored by whatever command is running. So most of them are blue, because mostly it's the UA command. But we have some little suspicious things here. So here is the left side of one of our gaps. And then we see there's this migration task sitting here that is running. First we have UA running, then we have the migration task, and then we have nothing for some time afterwards. So migration is a task that preempts other tasks. So you have a running task, the migration task wakes up, it preempts the running task, and pushes the other task off some other place. So it's used for some kinds of load balancing. So then we can ask ourselves, why are we doing load balancing? We have n threads, n cores, everything should be fine, no need for load balancing. So now we can look at this stepper thing. So stepper is going to go through each of the events in the trace and show you what's happening on each of the cores at each time. So we have, these are the core numbers up to 127. The thing to the left of this bar is the running task, and afterwards we'll see the waiting task will appear over here to the right. And so you can see at the current situation, I don't know, the machine looks perfectly happy. Everybody's running on their own core. Everybody's making progress. So that all looks fine. On the other hand, if we look down here at the bottom of the screen, then we can see that the current event is something called sched move NUMA. So this is the NUMA balancing of the kernel, and the idea is that the kernel has been monitoring the accesses that the task has been making on other NUMA nodes and has decided that would be a better idea for one of these tasks. It shows you which one here, this one here, to move from where it is right now, CPU 1, off to CPU 3. And this is a move. Nobody's going to come back, so you can just understand intuitively that this might cause some problems. So we can just step through here. So here we have a task you see on core 1. So it's waking up, this migration task. Now it has woken up. Now it's going to preempt that task there. So we have this little red and green thing. Red is where the thing used to be. Green is where it is now. And there's a little problem with the display here. But basically, our migration task has preempted our UA task. And then the next step is that our migration task will send the UA task off to its new home. And what's going to happen in the future is the migration task will go to sleep, its work is done. And now we're stuck with these two tasks over here on core 3. And for a certain amount of time in the future, those two tasks are going to be running half as fast, basically, as everyone else, because now they're sharing the core, whereas everyone else is able to run by themselves. So what's going to happen is those two tasks, this application is going to synchronize regularly, and those two tasks are running slower than everyone else, and so everyone else will now have to sit there and wait for those two tasks to complete. So it's not just those two tasks that are impacted from a performance point of view, it's everyone who's going to get slowed down. And so that really slows down the whole application. So basically, NUMA balancing, I mean, we had these two issues I mentioned at the beginning. We had work conservation, we had locality. NUMA balancing is supposed to improve locality. For our UA application, we saw that locality was important, so it might seem like a good idea to do NUMA balancing in this case. So there are two kinds of NUMA balancing. One of them will swap tasks on different sockets, so that's sort of not a problem from a work conservation point of view. One of them goes in the place of the other, and so they're all able to continue running fast. But what we had in our case was this move NUMA. So we have one task, it moves over to some other socket that's already full of other tasks, and so it introduces overloads. So with this NUMA balancing, we have lots of costs. We have to observe the situation, we have to make decisions, we have to do the migration. We might get some slowdown for our particular task that is going to be sharing with some other task on the same core. And then, as I mentioned before, we have this synchronization bottleneck. So that's our hypothesis. We just looked at one of these gaps to see, and it turned out to seem like a NUMA balancing problem. Now we can go back to datagraph, and datagraph can also tell us about some of these load balancing events. So we'll look at that. If you add the events argument, so this graph just shows you where our three gaps are, so you can kind of highlight on those positions. And if you give it the events argument, then it will add some arrows for different kinds of balancing events. And so basically what we have over here, we have a bunch of NUMA balance. We have one NUMA balancing event on the far left, another one here, and then we have some other kinds of task migrations that are basically cleaning up after the NUMA balancing situation. But there's a whole bunch of things that get moved around at the point when it decides to do NUMA balancing. So this is the fast run. This is a zoom in on the fast run. This is the complete fast run, so you can see lots more events are happening at different points, but you can see these two places that we highlighted at the beginning. Here we have at 5 seconds, we have a bunch of NUMA balancing, and here at 17 seconds, we also have a bunch of NUMA balancing. And those are the places where there was those lines and things were moving around on the machine. And then if we look at the slow run, then you can perhaps observe that things are moving around a lot more than one might have expected. Again, we have these green things, which are the various occurrences of NUMA balancing, and then we have the task moving around afterwards to kind of clean up after in some way. So now we may feel fairly confident that NUMA balancing is not really the ideal situation for this application, and so we can try just turning it off. Fortunately, you can do that from the user level, so it's quite easy to experiment with. Now we get that all the tasks just sit in the same place, and we get the performance of around 20 seconds that we expect. So here's the summary. The sort of pinkish ones are the performance with the NUMA balancing that I showed before, and if we remove the NUMA balancing, then it's pretty much almost flat, probably because, I mean, they're all just, the tasks are all staying in the same place all the time. So in conclusion, basically to really understand what your scheduler is doing, you have to kind of zoom in and see what its decisions it's making at each point. There seem to be different things that one can look at. They provide complementary information. They can help you figure out this is the part you should be studying. I presented this and like I already knew the answer to, so I could just go directly in the right direction. So my experience is more that you have like some kind of performance problem and you really just have no idea. I mean, you look at the graph and you try to zoom in and you try to find the right perspective on things that will show you some kind of patterns. Because sometimes, like if you sort the cores in a certain way, then you'll see just random nonsense. And if you sort them in another way, then some kind of patterns of concerns will appear and so on. So these three tools I have found, the ones I've talked about, I've found to be helpful. I think ultimately what I would like is what I mentioned here, a domain-specific language for creating graphs. There's many other different kinds of things that you might like to have highlighted, and it's a bit tiresome to have to write a new tool for every single one of them. So it'd be nice to make it more programmatical. Another question is scalability. So mostly being in academia, mostly I just work on like benchmark suites. These are real applications, but they've kind of been, they have data sets that are kind of understandable and so on. I don't know if any of this is usable in the real world for solving real problems or not. If someone wants to try, I would be happy to hear from you. As the graphs get bigger and bigger, it takes some time. You may like to get some coffee while your graph is being made. How to make things more configurable without inundating the user with command line options, and so on. So here's the URL for everything. So thank you.
Do we have any questions? No. All right. Okay, this is a long one.
Do you believe there will be applications for this? Oh, thank you for the presentation. Fantastic software for GPUs when they have more and more cores.
Yeah, so I've already gotten that question, and I don't think there's any trace command stuff for, it's too much proprietary stuff. There's no events, so I can't make the events. Or maybe some of you out here can make the events for me, but I only organize events that other people have made.
Thank you.
So it might be a bit on the side. You talked a lot about graphing, but also you have done some work on the scheduler to improve it. So what about now with chiplets, where you also have the cache, where just moving between cores on the same NUMA node? Or the other thing is also look at it regarding to cache, and the other is how much can you trust the UEFI firmware to? Because I've seen a number of times where the NUMA nodes is not, they say they're equal, but they're not. So can we get any help from the UEFI to where do we schedule the threads? And the other thing is it going to be harder now with the PE cores now and chiplets?
Okay, so that was a lot of questions.
Sorry.
So
Sorry.
chiplets, so we have some AMD machines, Zen 2 machines, and we've looked at that. So you can get the same information. We haven't looked that much into different. Mhm.
For Epic Rome, you can set, in the BIOS and most things, you can set the NUMA node to be on L3 cache. So 256 CPU, 128 cores machine will have 32 NUMA nodes because of the L3 cache NUMA. So then you have the chiplet separation as well.
Okay,
Yeah.
but I mean, that's not really my concern. My concern is to get the information to you in an understandable format. So we've definitely done experiments on AMD machines, and it was understandable for the user. So that's about all I can say about that. For the P&E course, that's something we're interested in looking into. We've ordered a machine. It hasn't shown up yet, so we haven't done any experiments yet. And then you asked about some other things that I think are not so relevant.
But it was interesting that you had a task being moved to a NUMA node because it's been there before, and then it evicts another task that's been running there. It was also, it's an odd behavior somehow.
Yeah, I mean, this NUMA balancing thing, I don't know. I don't know if people are, someone is knowledgeable about it, I'd be happy to hear from you at the break perhaps or something.
Hard if you don't know the future.
Yes, yeah, that's certainly the truth, yeah.
You just
But
have to do
mostly
the
I've seen
now.
strange behavior resulting from NUMA balancing rather than desirable behavior. But maybe that's just because I've only really investigated the strange ones and not really the ones where it was successful. Okay, thank you.